physics. And our first speaker is Zijian Wang. He will talk about interesting works on fractional quantum states and decoherence.
Okay, thanks. I'd like to thank the organizers for organizing this wonderful workshop and giving me the opportunity to give a talk here. And today I'm going to, by the way, I'm Zijian Wang from Tsinghua University, and my advisor is Professor Zhong Wang, who is the next speaker. Today I'm going to talk about fractional quantum Hall states under decoherence. And this work is done during my visit at Ehud Altman's group in Berkeley. And hopefully we will post it on arXiv soon. As we all know, in recent years, there has been a lot of great success in creating topological phases of matter and other interesting quantum phases in these artificial quantum platforms for quantum simulation and quantum computation. This includes the superconducting qubits, read-begetting arrays, and trapped ion systems. And one big feature or challenge of this platform is that they are noisy. So one basic question is: suppose you want to prepare some state. Can I guess some sticker? Oh, yeah. For example, you want to prepare some topological state psi, but your preparation is never perfect, so noise will happen. So you always get some decoherent state, mixed state rho. So and then we want to know whether this mixed state is still in the same phase as the target state, or whether the state is ruined by decoherence. And it turns out in some cases there is a threshold above which there is a transition where the topological states you want to prepare is ruined. And perhaps, so operationally, that means if you want to encode some information in the code space, say, then above some threshold, you can no longer decode the information. Perhaps the most well-known example is the decohered Tor code, where it's found 20 years ago that there is a threshold in Tor code. And more recently, like 2 years ago, it is pointed out that the ability to decode is actually an intrinsic property of the underlying many-body mixed states. And several diagnostics are proposed to diagnose such mixed state topological order and the mixed state phase transition. And inspired by these developments, nowadays there is a large landscape of mixed state phases of matter. And I also did several works on this. So why is this interesting topic? One fun aspect of this is that it brings together quantum information, quantum many-body physics, just like this workshop. And from the quantum info perspective, we can use a perspective from many-body physics to help us gain a better understanding of how error correction code works, like in Ethan's talk and Tibor's talk. And from many-body physics side, there are a lot of new possibilities and opportunities to realize new phases of matter that is beyond the conventional paradigm in equilibrium physics. For example, as I have said, there will be even the very notion of phases and phase transitions need to be re-examined in mixed states. For example, you can no longer use the ordinary observables or correlation functions that are linear in density matrix to diagnose such phase transition, because all you do is applying a finite depth local channel, and by Lieber-Robinson bound, all such linear observables must change smoothly. So to diagnose such a phase transition, you have to use information quantities that are nonlinear in the density matrices. And although such diagnostics are very unconventional, there's still a clear operational meaning of this, that it's the ability to decode. So also there will be new patterns of long-range entanglement in mixed state, which allows one to use to realize novel types of topological order and anyon theory. Oh, by the way, the blue ones are just works that I'm along the author list. And furthermore, there will be the notion of symmetries is also enriched in mixed states. There will be strong versus weak symmetries, and there will be new types of symmetry breaking and new types of SPT, etc. So, and today I'm going to talk about the fate of quantum Hall states on the decoherence through the lens of mixed state phases matter. So first, what is fractional quantum Hall? It's the first realized example both in theory and in experiments of topological order. So the setup is very simple. You have some two-dimensional electron gas under some very strong magnetic field. So we know that the then electrons will form lambda levels, which has huge degeneracy. And it is found that only when the lambda level is partially filled, the state still we still observe some gap states. So that has to come from interaction. It's a strongly correlating phenomena. And what is first observed is that about near some fractional filling in transport experiments, some Hall plateau is found for Hall resistivity. And then after this observation, a lot of theoretical understandings are developed. For example, it is pointed out that such fractional quantum Hall states have a topological degeneracy, means that the ground states are degenerate when you put the system on a torus. And furthermore, there will be gap excitations that have anyon statistics. And also these excitations will carry fractional charges. And furthermore, many of these fractional quantum Hall states are chiral in the sense that they have chiral edge states. Okay, and now we are interested in the question, what if these quantum Hall fluid are subject to some external noise, which may, for example, arise from the interaction between the sample and those electrons in the metallic gate. So first, let me specify the question a little bit or phrase it in a quantum info language. So from a quantum info perspective, the question is how good are fractional quantum Hall states as quantum codes? That means we can, because it has non-trivial topological order, we can encode information using these quantum Hall states. There are two ways. First, because of the topological degeneracy, we can encode the information in the topologically degenerate ground states on a torus to realize quantum memory. And furthermore, if you have non-abelian quantum Hall states, you can also use the fusion space of non-abelian anyons to encode the information. And that's the program of topological quantum computation. So in both cases, we are interested in the question is, how resilient is this information? And also from the many-body physics perspective, you may ask, since there are a lot of works on mixed state phases, so what's interesting about quantum Hall compared to the previously studied examples? So the most studied examples of mixed state phases start from a ground state of commuting projectors because these are simple and also we can derive a static description starting from these models. However, these models also have strong limitations in the sense that they cannot realize chiral topological orders, but quantum Hall can realize chiral topological orders. And also, there is some additional feature in quantum Hall that is the UN symmetry because of charge fractionalization. So there's a global UN symmetry that enriched the topological order. And we are interested in whether the interplay between the chirality, the UN symmetry, and decoherence can give rise to novel mix. And another important question that is not very well understood is that what's the behavior of non-abelian anyons under decoherence? So that's related to this question. So because most studies mainly focus on abelian topological orders up to now. Oh, sorry.
So can you raise the volume?
Yeah. So can I think that fractional quantum was taking to the system already?
Yeah. So sorry. For noise? What?
In fractional quantum world system, we already observe in solid state systems such as two that system under strong magnetic field.
Yeah.
And in a solid system, it suffer from noise due to environmental interaction. So can I think that such experiment at the fractional quantum world state realizing such experiment will suffer from noise?
Yeah, they will suffer. In general, they will suffer from noise. So there will be two kind of noise. So one type is thermal noise. So these are suppressed in low temperature. So that's the goal of topological quantum computation because thermal noise are suppressed and then the information is protected. But sometimes the noise can be more than thermal noise because, for example, when you add a metallic gauge on your sample, this will have some external noise that this cannot be simply treated as thermal bath. So that's why we should considering such decoherence effect. Thanks.
Since realistic experiments done on fractional systems are actually subject to these consequences, right? So can you sort of should you think of already existing experimental fractional quantum Hall states as being something that is already under the presence of that noise?
Yeah, sure. I think that's true, but there hasn't been a topological qubit hasn't been convincingly realized in such system, but there is hope. There are some recent exciting developments, graphene quantum Hall system, which may be relevant in the future.
Maybe I think what Jicheng is asking is, we already have a fractional quantum state, not necessarily a topological qubit though. So they already limit this physics. But maybe my comment is that in a condensed layer systems, there's a coupling to the phonons, for example, to give rise to this. But like when we talk about incoherence in this physics, coherence is happening at very UV and lattice level scale, while coupling to phonons is very IR scale. So I think there will be some difference. Yes, but although like maybe things will RG into the physics.
Oh, for phonons, I think phonons can be regarded as part of the thermal bath. So they happen in the IR, but there can be also other UV type of noise. Yeah, and also a related comment is that such mixed phase phenomena can, as I have said before, cannot be detected just using the conventional condensed matter techniques like transport phenomena and other correlation functions, but need to be detected using information quantities, which has to do with error correction. So after you realize the topological qubit, you can really detect such phenomena. Okay, so let me repeat. The question is, so the question we are interested in is whether the future roles of non-abelian anyons remain well defined. Okay, so now let me specify the noise model and the quantum Hall states we want to study. So in this talk, we will mainly focus on two types of states. The first is the most well-known, the 1/m Laughlin state, which is abelian, and another is the Maurice state, also known as the Fafin state, which is a non-abelian quantum Hall state, and also the first realization of non-abelian topological order. So our decoherence model, we just choose focus on a very simple and natural one. That is the dephasing noise, which is described by this simple Lindbladian, where the jump operator is just the particle density. So this type of noise can naturally arise in experiments from density-density interaction between the system and the environment. Okay, so to characterize such decoherence-induced transition, we need to use information quantities. So, for example, the von Neumann entropy, coherence information, and relative entropy. But since these von Neumann quantities are usually very hard to calculate directly, we will first study the simpler Renyi versions, which is simpler. So in part one, let me start from the decohered Laughlin state. So here's a brief review. So this is the Laughlin wave function, which is a lowest lambda level wave function at filling 1 over m. Here, for electrons, m need to be an odd integer to keep fermionic statistics, and has very, very interesting properties. For example, the ground state degeneracy on torus is m. And also, quasi holes and quasi electrons carry fractional charge. And on the edge, there will be some chiral boson mode on the edge. So it turns out all these properties play crucial roles in the decoherence problem. So let me first show you the results. Here's the phase diagram. And we find that surprisingly there exists some critical filling, which for Renyi-2 quantities, it's 1/4 filling. And also because the fillings are not arbitrary numbers, but need to be some odd denominator state. So that means, so for example, so we find that below the critical filling, there is a KT transition at some threshold, which separates the topological ordered state. And also above the threshold, the state has some critical behavior, and we call it a critical phase when increasing the noise. And above that means, for example, for true replicas, that means 1/5 or 1/7 filling. And on the other hand, above the critical filling, for example, for 1/3 Laughlin state, there is no threshold, and the states always remain non-trivially topologically ordered for any finite strength of defacing, and only the topological order is only corrupted at infinite defacing noise when the system becomes fully classical. Okay, so that's a surprise to us. That means the topological order is extremely robust at above the critical filling. So to show this result, we will use two complementary approaches, the plasma analogy and the effective field theory description. So let me first review the plasma analogy for pure Laughlin state, which is also proposed by Laughlin. So for example, if we just take the wave function, Laughlin wave function, and do the inner product, that is the wave function norm square, and we find that it takes the same form as the partition function of a two-dimensional Coulomb gas, where all the particles carry positive charges, square root of 2m, and there is also a neutralizing uniform background. So that's the partition function of that plasma. And since it's a stat-mag model, we can do people can do Monte Carlo, and it is found that for m smaller than 70, which is a very large number, the plasma is always in the screening phase. So here screening means if you insert some test charge in the plasma, the Coulomb potential of that test charge will be screened by these dynamical charges. And there has been a lot of arguments about how these screening properties of the plasma imply the topological order, topological property of the two-dimensional states. Okay, so for Renyi-2, so for the Laughlin states for any m smaller than 7 is describes some topological order. Okay, so we are interested in Renyi-2 quantities. The simplest one is the purity. We have two replicas. Naturally, we will get two copies, which are represented by two layers in this picture. We get two layers of Laughlin plasmas, which are coupled together by decoherence. So here's the coupling, which introduce some short-range attraction between the layers. So that is because that's very natural, because defacing noise is going to suppress the off-diagonal elements in the density basis. And here the two copies corresponds to the particle positions in the kit and broad space. So So decoherence will force the two particle positions to be identical in the two layers. That describes dephasing. And to give an intuition, let's first understand the two limiting cases. So first, when there is no decoherence, mu is the decoherence strength, then the two layers are completely decoupled, and each of them are independently in the screening phase. On the other hand, on the other limit, when mu is infinity, so the states become fully diagonal, and that means the two layers, the particles in the two layers form tightly bound pairs. So in this case, it's no longer screening. And the question is if there is a transition in between. So to answer this question, let's start from the strong decoherence limit, where all the particles form tightly bound pairs, and perform a Dirichlet-Dawes type argument to see if there is an instability. So we start from this configuration and apply a small perturbation, which means we just unbind one of such pairs to have some unbound charges with distance r. So that corresponds to the infinitesimal fugacity limit. So let's first estimate the energy cost of such perturbation. And naively, because we start from some charge uniform distribution, and then we do such splitting, and we will create a particle pair. So then there will be a Coulomb interaction between them. That's the energy cost. So, but in our example, in our model, it's actually slightly more complicated than this. So that will correspond to the original Dirichlet-Dawes scenario. But in our model, since we also have these large number of tightly bound pairs, which also carry charge, so they will move around to try to screen these interactions. But since they can only move in pairs, they cannot fully screen the interaction. The best thing they can do is to reduce the energy cost by half. So that's a heuristic argument, but we can rigorously show this. And then we need to, we assume the distances of all we estimate the entropy gain from such perturbation, and that will be 4 log L. And then we immediately find that for m smaller than 4, the entropy always wins. So charge always tend to unbind for any finite dephasing. That means the plasma is always in the screening phase above the critical filling 1/4. On the other, sorry. On the other hand, below the critical filling 1/4, there will be a KT transition separating the screening and partially screening phase. Okay, so now the problem is we are actually not interested in this whole 2D phase diagram because the physically relevant states only live on these discrete lines, vertical lines. These are the fillings that correspond to Laughlin state. Here, I also draw these even denominator states. They correspond to the bosonic Laughlin state. Okay, so obviously the fully screening phase should correspond to the topological ordered phase because without, that's the phase that is smoothly connected to the states without decoherence. So that's a Laughlin state. And the curious part is what is this partially screening phase? What do they correspond to? And it turns out they correspond to some critical phase, which has some power law correlation, which I will explain now. Why is it critical? So the simplest way to diagnose such critical behavior is to use the so-called Ren-2 correlation function, which is defined in this way. So here, so also a closely related quantity is the Ren-2 relative entropy, which is the log of the Ren-2 correlation function. So both quantities diagnose the distinguishability between rho, the decoherent Laughlin state, and another state which obtained from rho and inserting a pair of particle, hole pairs. And so it's quantifying the distinction between two such states. And so it's a natural generalization of the off-diagonal long-range order in pure states. It characterizes whether the charges proliferate in such states. So it has been used to, for example, diagnose the strong to weak symmetry breaking. That's a note for experts. In the topological ordered phase, the range, because it's short range correlated for any local operator, so it does for the range 2 correlations. There is a finite correlation length. However, we find that for the above the threshold, the range 2 correlation has some power law decay. So which we can derive for the simplest case now. This is the maximal dephasing, where all the particles form tightly bounded pairs. And because they form pairs, then we can simplify the description to a single component Laughlin plasma, where Q equals 2 times square root of m. Okay, and then we can, and then this single component plasma is in the screening phase of this single component plasma to argue why such power law correlation arises. So we can simply take the form of the Laughlin wave function to derive such an expression for the range 2 correlation, where eta and eta prime are the insertion of these electrons. Okay, so here's the expression, and actually it has a static interpretation. If we just add a term and then subtract it, which does not change the result. And then after we do this, everything in the red box has a very beautiful static interpretation. So that corresponds to the free energy cost when you insert a pair of test charges into this plasma at locations eta and eta prime. So because the first term just corresponds to the Coulomb interaction between these dynamical charges, and the second term is the Coulomb potential for these dynamical charges from the background, uniform background density. And this term, the third term is the Coulomb interaction between the dynamical charge and the test charges. And this is the Coulomb potential for the test charges. And this is the Coulomb interaction between the two test charges. So we need to add this term. And because the plasma is screening, so the interaction between the test charges will be fully screened. That means this whole quantity in the red box approaches some constant, some finite constant when eta at large distance. And then the range 2 correlation is simply proportional to this term, which shows power law decay. Okay, so this power law behavior also holds in the whole critical phase, which I will not show here, but it will become clear later. But this result is a little bit surprising to me at first, because we start from the Laughlin stage, which only has short-range correlation for local operators, and then we apply such very innocent dephasing noise, then suddenly it has power law correlation. So why is that? Where does this power law correlation come from? Actually, that is related to the quasi-long-range order of composite bosons pointed out by Gervin and McDonald. Such correlation actually already exists in the Laughlin states. So what they pointed out is that although for electrons, which are local operators, it has finite correlation length, but if you do such a non-local transformation, if you attach a non-local phase factor to the electron operators and form a composite boson operators, these composite boson operators will have power law correlation.
But this correlation is happening in the range 2 version. So why is it couldn't it just happen naturally, like in the double space?
Yeah, good question. So so this correlation happens naturally in the double space, but that's non-local correlation. This composite, so composite boson, so this correlation, composite boson already have, and at the physical level, and yeah, right, and also in the for the range 2 correlation, composite boson also have power law correlation, but that's non-local. But after applying the dephasing noise, the bra and the catch, the density matrix become fully diagonal, and the flux attachment phase factor cancels between bra and cat. And then the non-local correlation function becomes a truly local correlation function. Correlation.
So are you implying that if you want to get quasi long range correlation in this range two, there must be a quasi long range order, like hidden quasi long range order already previously?
Oh, that I'm not sure, but in this case, it exists. It's just an interpretation for this case. So I'm not sure if I have already explained it clearly. Let me repeat this. So before decoherence, there is already hidden power law correlation for this linear correlation and the range 2 correlation. But after dephasing, this hidden quasi-Lagrange order will become the true quasi-Lagrange order because the flux attachment phase factor just cancels due to dephasing. And so that explains the critical behavior. And then the next question is, does the KT transition really correspond to the breakdown of quantum memory? That's our initial question. And although for quantum Hall states, there is no known explicit decoder, but fortunately for us, it is pointed out that there is actually an intrinsic measure of quantum memory that is known as the coherence information, so which quantifies the ability to decode even without an explicit decoder. So it is defined in the following. So for example, we want to encode some information in the code space using such encoding map V. So here it's the input, here is the output. And we can alternatively represent this as entangled the pair between some reference qubit and the system. So that's the initial state, describes the encoding map. And then we apply some noise channel to the system Q, and we get a decoherent state. And the coherent information is defined as the entropy, the volume entropy of Q minus that of RQ. So it quantifies the amount of encoded information that can be recovered after decoherence. And it can be proven that it's upper and lower bounded by the dimension of the code space. And also it is pointed out in this paper 30 years ago that one can do perfect error correction to the noisy state if and only if the coherent information saturates the upper bound. Okay, and to diagnose such quantum memory, so of course we need to put the system on a torus, but then it's the Laughlin wave function on a torus looks horrible, so which discourages a direct plasma analogy. So we need to use the alternative approach that is a field theory approach, and we can use a field theory to calculate the range 2 coherent information. And so to use the field theory, our starting point is the celebrated bulk boundary correspondence, which was proposed by Moore and Reed in 1989. That is, the bulk wave functions of quantum Hall can be expressed as correlators of the edge theory, which presumably is a CFT. More precisely, it's the conformal blocks of the edge CFT. So in the case of 1 over m Laughlin state, the edge theory is U1 level m chiral boson CFT. And the electrons will correspond to these chiral vertex operators on the edge. If you create an electron in the bulk and drag it into the edge, it corresponds to insertion of such an operator. And the anyons are in one-to-one correspondence of the primary fields of the CFT. There's m of them, which correspond to m anyons, which includes the quasi-hosts and their fusion. So now we can imagine doing a space-time rotation, and then the wave function of the bulk can be obtained by such correlators, which each of them correspond to the electron operators, and here it is a neutralizing background charge to ensure the result is non-zero. And you can straightforwardly verify that this is indeed the Laughlin wave function. And here I'm just re-expressing the correlation function to be an integral between integrate over the density coupled to the chiral boson field phi. So the last step is just rewriting. But then we can take this expression to derive our desired result for the Ren2 quantity, trace zero square. So here's the result. And when you're doing the product, you combine the chiral boson field phi and the anti-chiral part phi bar to become a non-chiral field phi. So here phi 1 and phi 2 are non-chiral boson fields. And also because we have two replicas for Ren2 quantities, we will obtain two such non-chiral boson fields. And the purity just corresponds to this effective field theory for these two non-chiral bosons. And then each of them is described by a free boson CFT, but they are coupled together through this form, mediated by the density. And so what is this coupling? We can first look at the limit where there is no decoherence, mu equals 0. Then the density just serves as Lagrangian multipliers for this phase field, for this boson field phi, which completely gap out the bosons. So that's why the Laughing states are gapped. And the effect of the decoherence, now at decoherence, the effect is to suppress the charge fluctuations, the density fluctuations. And since this boson density field are conjugate to the phase field, when you suppress the charge fluctuation, you will release some of the phase fluctuations. And also but since the dephasing only suppress the fluctuation of this relative density, so part of the phase field is still fully gapped, but part of the fluctuations can be released. We call it phi plus and phi minus. So in the end, after we integrate out the gapped degrees of freedom, the purity is simply mapped to the partition function of the Sine-Gordon field theory, which has only one component. That's the phi minus field. Again, we get this phase diagram. Okay, so the advantage of this framework is that now we will have writing the Laughlin wave functions of a torus. They still correspond to this correlation functions of the chiral boson CFT. But this time, because we live on a torus, the field phi can have different winding numbers. So we have m of such choice where n equals 0 to m minus 1. That corresponds to the m degenerate ground states on the torus. And naturally, the coherence information we want to calculate, so has this form. And so naturally, the numerator and the denominator will correspond to the partition function of this CFT, of this field theory, with different combinations of winding number signatures. So here's the final result. After we translate the winding number of chiral bosons to this, the final boson field phi minus, we get a simple expression for coherence information. So in the numerator, corresponds to combinations of partition functions with, so let me first do the denominator. The denominator corresponds to partition functions, sum of partition functions with different twisted boundary conditions of the phi field. And the numerator corresponds to partition function with tested boundary condition of dual field theta. So theta is the dual field of phi, which means in canonical quantization, the phi and partial theta form canonical conjugate variables. So then we immediately get from T duality that at mu equals infinity, there is no, because there is no cosine term in this limit. And the theory is simply a compact boson CFT. And due to T duality, these two twisted boundary conditions should have the same free energy cost. Then the numerator and denominator are equal to each other. So the coherence information is exactly 0 as expected in this case. However, for any finite mu, then we need to compare the free energy cost between these two different boundary conditions, and we will find that, for example, in this topological ordered phase below the threshold, the cosine term is dominant and gives out the phi field. Then the twisted boundary condition of phi will have cost order L free energy. Then that means in the denominator only the term with n equals 0, that is untwisted boundary condition, will have order 1 contribution. Others will decay exponentially with system size. So then we get the coherent information is log m. However, the surprise is that above the threshold, but for still finite mu, in this case, this corresponds to a critical phase. The cosine term is irrelevant, but still we find that we can do perturbation theory and find that it still leads to additional order 1 free energy cost for the twisted boundary condition of phi. And that will lead to a finite coherent information which is between 0 and log n. So that's very different to the decoherent torque code. So that's here's a plot for the coherent information. So above the critical filling, there's no threshold, so it stays log the maximum value and only jump to 0 at infinite decoherence. And however, for log links, for below the critical filling, there is a KT transition corresponding to and there is a finite jump of the coherent information at the threshold to some finite value, and then decays smoothly within the critical phase and decays all the way to 0 only at mu equals infinity. That's in sharp contrast to the decoherent torque code, where the coherent information jumped to 0 at the threshold. So that's the Oh, good question. Because actually we see that the bounds of the coherent formation is between minus log m and log m. So for any classical system, coherent formation can only be negative. So as long as it's positive, it means there is quantum memory. So that's the operational meaning for the critical phase, so that it has partial quantum memory, even above the threshold. Okay, so the above are all the results for the Renyi-2 cases, but as I said, the more meaningful quantity are the von Neumann quantities, so which correspond to the limit where the replica number n goes to 1. But although we can perform the same argument for any Renyi n quantities, this replica limit is ill-defined. So what do? And alternatively, we just directly use the von Neumann entropy to study the transition, which is hard. So we only have some partial results. For example, the simple thing is still the maximal defacing scenario, where the density matrix is fully diagonal, and we can characterize this critical behavior with some more meaningful information quantities, such as the Whiteman correlator, also known as the E1 correlators. So which also have such power law correlation. One can instead use some fidelity correlation. They all give similar results. And that means the fully decoherent state is still critical. But now we are interested in whether there still exists some critical filling. So whether there is a KT transition at some fillings or otherwise. And so the way we do it is to examine the stability of such of this critical state at maximal defacing. We do a strong decoherence expansion, where rho naught is the fully decoherent state, which is diagonal, and here because this part corresponds to the density matrix where only have one off-diagonal element, and do such expansion and examine each, and then we can calculate the von Neumann entropy perturbatively and see whether there is still a Cauchy-Stolitz type instability relating to the proliferation of off-diagonal elements. So this calculation, the direct calculation will be hard because for von Neumann quantities, there is no stat mech description. But we managed to find a upper and lower bound for this quantity, which does have both bounds will have a stat mech description. And that's how we can prove there still exists a critical filling that is between the 1/8 and 1/4 for the von Neumann case.
So you get stat mech description by doing a e to the minus mu expansion.
After doing the e to the minus mu expansion, there is still no stat mech description, but then we can bound this quantity using a stat mech quantity.
How does that getting bound?
Just using several inequalities like Jensen's inequality, Cauchy's inequality, and both bounds, both the upper and the lower bounds correspond to the stat mech model. Okay, so that's all for the decoherent Laughlin states. Now we go to the more interesting part. That's the decoherent non-abelian quantum Hall states. So the most important, the most well-known one is called the Moore-Reid state. So here's the Moore-Reid wave function, also proposed in this paper, where there's still a Laughlin gestural type factor, and there's also a Fafin part in front of it. So here's the definition of the Fafin for anti-symmetric matrices. Here, to ensure fermionic statistics, M need to be an even integer. So the Moore-Reid or Fafin state describes a non-abelian topological order. Also, it is a strong candidate for the at M equals 2. The Moore-Reid state is a strong candidate for the observed Hall plateau at filling 5 halves in gallium arsenide. Okay, so let me review the construction of the Moore-Reid state. So again, they are constructed using conformal blocks of the edge CFT. So let me first review the notion of conformal blocks. So suppose you want to calculate some endpoint correlation function of the CFT, and sometimes you can factorize it into the holomorphic and anti-holomorphic part. So the holomorphic part is known as the chiral conformal block, and sometimes you cannot simply factorize it, but you need to decompose them into a summation of such factorization, and each component is known as a conformal block because they are like the building blocks of the any correlation functions of. And so in this in the paper by Moore and Reid, they first observed that such construction exists for the non-Laughlin state, and then they said, why not start from input another CFT and design new quantum Hall wave functions? So here's the construction. We can start from the Ising CFT combined with a chiral boson CFT, which and here we can show that here and the electrons can correspond to such operator, which we can show for M for even M, it's indeed fermionic operators. And again, anions are in one-to-one correspondence of the primary fields of this CFT, which are mutually local with the electrons. And you can examine the anion statistics of these, and they are have trivial breeding with the electrons. So then we can get the wave function is actually constructing this way, again, by of this CFT by inserting the electron operator. And so that's the electrons, and the Cauchy holes, the fundamental Cauchy holes, in this case will correspond to this operator. So here this factor means, so sigma is the order parameter for the Ising CFT, and phi is the composite chiral boson operator. So this factor means the fundamental Cauchy holes carry even smaller charges than the Laughlin Cauchy hole. It's the charge is 1/2m. Okay, and the more exotic property of such Cauchy holes is that they are non-abelian anions because of non-abelian fusion rules of the sigma operator in the Ising CFT. So the simple case to see such non-abelian fusion is when you have 4 Cauchy holes, and the 4-point correlation function will have 2 conformal blocks. and they will be correspond to two degenerate states with 4 quasi holes. That means the 4 quasi hole states will span a two-dimensional degenerate subspace, which is known as the fusion space. So in the topological, from the two-dimensional topological state side, so the two states in the fusion space correspond to when two Ising anyons correspond fuse to an identity anyon, or they can fuse to a fermion instead. Then because such information is stored in a very non-local way in the fusion space, it can be used to encode a topological qubit using the fusion space of such non-abelian anyons. So that's proposed in topological quantum computation people. And so now the question is clear. The question is whether the fusion space loses integrity under decoherence. That is equivalent to say whether the non-abelian anyons are still well defined. So we can take from this conformal block construction of the Fafin state, of the Mori state, and again, using the same trick to calculate the purity. So now,
Density perturbation, right?
yeah, still defacing noise. Thanks. And here it corresponds to a very complicated correlator, where epsilon is the energy operator and phi is the non-chiral boson field. And also because we have two replicas, we have an Ising square and U1 square CFT. So, and such correlativity. And also the effect of decoherence is to introduce a fugacity of unpaired correlators between the two copies. And so this quantity looks quite complicated. And the basic question we're trying to ask is that we start from we can take the CFT as a starting point and ask how the insertion of this extensive number of operators change the behavior of this field theory. So how should we think of this weird partition function? And one way to think about it, so it's very awkward. Yeah, maybe it can be turned into a more familiar or more friendly form by doing Bosonization. So we can first Bosonize the Ising square CFT using the Bosonization dictionary. And after the Bosonization, the CFT action can be, the CFT can be described by this simple action, where this is from Bosonization of the Ising square, and this is the true compact boson CFT we start with. And then the purity corresponds to this quantity. Still look quite horrible. So how should we think about it? So there are two ways. One way is that we first integrate out this field, and then we are only left with the integration of these locations of insertion of such local operators. That corresponds to the plasma analogy. If you recall in the Laughlin case, that's how we get the plasma analogy, where the dynamical variable is the positions of these plasma charges. And alternatively, we can integrate out. Okay, so for Mori state, a plasma analogy is actually derived in the paper by Magnuson and Nayak. But it's quite complicated and does not serve as well when we try to understand the non-abelian anyons. It can give the threshold, it can get the phase diagram correct, but hard to calculate the coherent information in this way. So we use an alternative perspective by, that is, we can integrate out this first and then treat this as a field theory. So, but this field theory is still weird because it's not described by an action. So this part has an action description, but then we also have this operator insertions. So, but that's okay. We can still use field theory techniques to describe such a theory even without action description. So that is like in any other field theory, we can first analyze the symmetries. So there are a lot of symmetries. There is that's ZM symmetry, and a U1 symmetry for phi minus, and there is a at maximal defacing, there is also a UN symmetry, true UN symmetries for Ising square CFT. And that's also true non-invertible Quermes-Wannier symmetries. And then after analyzing these symmetries, we ask whether they are spontaneously broken by calculating the correlation functions. And then the correlation functions can be calculated using the plasma analogy. And then after using applying plasma analogy, we can show that many of these symmetries break spontaneously. So that's the result for the maximal defacing, which will help us gain an understanding for finite defacing case. Because at finite defacing, oh, maybe I delete this by mistake. So at finite defacing, we can perform a strong decoherence expansion. And then each term in the expansion can be regarded as a correlation function of this field theory, which is the infinite defacing case. And then using the knowledge that these symmetries break spontaneously, we can simplify the correlation function on this theory, which will allow us to derive an effective field theory for finite defacing, but finite but strong defacing. So then the expression looks simple. Here, let me tell you that phi matrix is the same boson field as in the Laughlin case, and the capital phi and capital theta are from the bosonization of Ising square CFT. And here, because of the UN symmetry breaking, they form a condensate of phi or theta. So they can be treated as a constant field, which only arises as a coupling constant of the Sine-Gordon theory. So that's the final result. So they will not change much for the phase diagram. We still get the same Sine-Gordon phase diagram. So the critical filling is still 1/4. And below the critical filling, there is a KT type transition separates topological order and the critical phase. But so that means for the UN sector, abelian UN sector, the result is just the same as the Laughlin case. But for the Ising sector, the result is different because even in this critical phase, while this term is irrelevant, it will still generate other relevant terms under RT, which gap out to the Ising sector. So Ising sector is always gapped as long as mu the defacing strength is finite. So that suggests that the non-abelian fusion rules are still preserved, but we need to examine this. So the way to examine is again by calculating the coherence information, but this time the coherence information is defined for the topological qubits encoded in the fusion space of non-abelian anyons. So let me remind you that the true states in this fusion space correspond to different conformal blocks. And the numerator and denominator again correspond to different combinations of conformal blocks. And they can be related to the 4-point correlation functions of the local primary field, theta, sigma, that's the order parameter, and mu, that's the disorder parameter. And again, using bosonization dictionary, finally, we can get a very simple result for the coherence information that corresponds to the correlation function for capital phi field. And then the result is that for below the threshold in the topological ordered phase, both the Ising field and the UN field are gapped. So coherence information is log true, which means the fusion space is preserved. And also, even in the critical phase, where mu is smaller than infinity, the this abelian field is gapless, but the Ising field is still gapped. So the coherence information is still log true, which means the non-abelian anyons is still well preserved, even in the critical phase. So, but only in the infinite defacing case, we get 0 coherence information.
Now, I guess like when you make manifold more complicated, like the number of the query information initial value is larger, and I guess probably behaves in the same way, but is it possible to see what how the calculation change if the underlying manifold is more.
Oh, good question. I think it doesn't change much. It's still using the same techniques, using Bosonization, you can get a similar result for correlation of file data. Yeah, thanks. And okay, so that means the non-abelian anyons are so robust. That's good news. Okay, so here are some future directions. For example, in our noise model, we just consider a very simple defacing noise, but there are some problems for that noise because it happens in the UV. For example, it can even create some excitations in a higher lambda level, which means the defacing noise does not leave the lowest level invariant. So that's a problem because the lambda level gap is huge. So in reality, usually such noise is suppressed. So we need to consider so-called low frequency noise, which stays in the lowest level. And for our calculation, we only, what we did is to calculate coherent information, which only serves as an upper bound for the decoding ability. So, but we do not have an explicit decoder. So we also need to construct noise models with an explicit decoder. Actually, we have some progress for these two problems, and we have some phenomenological noise model, which stays in the lowest level, which we know how to take the replica limit and obtain a decoder. Okay, and another question is, we get a result for the Maury state, but as you see, it's quite complicated. The complication is twofold. First, from the non-abelian topological order, and second, because of U-1 symmetry, there is a constraint due to U-1 symmetry, and that's why this expression does not have an action description. It re-exponentiate it because of the constraint. And also the result sounds weird. The non-abelian anyons are always so robust. So we can ask whether there exists a noise model where the non-abelian anyons actually undergo some transition. We also did some work on this and find another chiral topological order without U-1 symmetries, and we add a noise to proliferate the non-abelian anyons. We will find that in this case, there will be a transition where the non-abelian anyons are killed. Okay, the final question is, then let me leave it. So thanks.
I'm trying to understand what is a coherent information of a abelian anyons. So like if you turn on the decoherence, what is the physical picture? Like how should I understand you lose the coherent information of anyons? Does anyons not well defined, or how should I
what do you mean by
for example, like in math, it is I can see like trace of rho square. You can just calculate the value of trace of rho square, but what does it mean to lose coherent information in the anyons?
You mean abelian anyons?
Yeah, for like
I don't know what you mean.
One-third fillings without any decoherence. Fractional quantum, the Laughlin state is well defined, and we have a well-defined excitation that with having like holes or particles. But with the decoherence, you say you can have a transition in the information theoretical value of coherent information. But what does that actually physically mean?
Yeah, first I need to clarify that we do not define coherent information for abelian anyons because their fusion space is one-dimensional.
Oh, yeah.
So you cannot encode information using their fusion space, but we can encode their information on a torus using topological degenerate ground state, but not the abelian anyon excitations.
I see.
So the coherent information characterizes whether you can encode the information in the ground state subspace. While for abelian anyons, there is a transition which characterizes whether the abelian anyons proliferate or not. That means if you start from the ground state and you create a pair of abelian anyons and you do decoherence, and you ask after decoherence whether with the state without abelian anyons. So that characterizes abelian anyon proliferation, which can also diagnose such transition. So in the critical phase, So in the topological ordered phase, if, for example, if you calculate the relative entropy between two such states are described, in topological ordered phase, it will diverge linearly. That means they are very distinguishable. But in the critical phase, they only diverge logarithmically. And this corresponds to the Paul-Law-Ren-Yichu correlations. And you take a log, you get logarithmic divergent results. So they are less distinguishable in this case.
Nice. Thank you. One more question. Like you say you have a KT transition. And so what is a vertex? What is a vortex defined on this? For KT transition, you need the instability due to the vortices. And what are the vortices in this?
Oh, for KT transition, maybe you are more familiar with the KT transition in the XY model, but there is also KT transition in the two-dimensional Coulomb gas. So I'm directly using the Coulomb gas description. That's it natural here. And the two models are related because the vortices have two Coulomb interaction between each other, the vortex and energy vortices. So actually the vortex configuration of XY model can be mapped to the 2D Coulomb gas problem. So that's how they are related.
I see. So it's just proliferating all these.
Yeah, charges, unbinding charges. Hi.
Thank you for the nice talk. It is possible to use your theory to specify which state is stabilized at the 5/2 of the, 2-deck system, 5/2 of the Gallium system.
I think that's very challenging. I don't know. You mean to distinguish whether it's Fafin or particle Fafin or anti-Fafin? Yeah, I don't know. I don't think that we can do that. It's
Okay, I have two questions. First question is, can you apply the same formalism for all the Jane sequences?
Yeah, good question. I think so. Yeah, but there is a subtlety.
Then you can maybe all the particle pair and the higher fillings and yeah.
Yeah, so for Jane sequence, we can also first express the wave function using conformal blocks of the UNCFT, and then apply the same strategy. But there will be complication when, for example, the state it's non-chiral, then there will be complications because yeah, for chiral boson CFT, it's special because the Latinger parameter is fixed by kinematics. And for non-chiral ones, you have a non-universal V matrix, which can change the Latinger parameter. Then the result will be non-universal.
So second question is, all this coherent information is really the upper bound for the recoverable quantum information. And
yes.
and since you mentioned the whether topological qubit, the goal of topological qubit is having a quantum information without any active error correction. But in some sense, coherent bound is like kind of calculated, assuming that we can do like a really electron level quantum error correction. So if we have a certain coherent information calculation from here, and the thing is that we just have a topological qubit as envisioned by station Q, then will there be any hope to saturate that bound?
Yeah, good question. For this noise model, I can't imagine how to build a decoder. That's why I mentioned maybe we need other noise models, which is more realistic at first. And also, we do have noise model where we know how to build a decoder. Then we can compare.
So roughly, how does this decoder work? Because I feel like decoding has to be very, very UV scale, and I don't know whether we have such a control in the.
Yeah, if your noise
That's better.
model lives in the IR, for example, you consider energy penalty for higher level excitations, and then your noise model, the only thing you can do for noise is to create these quasi electrons and move them around, and they will be likely to trap in some impurity. Then for the decoder, we just need to do some measurements on the impurity to detect such excitations and try to pair up such quasi-electrons, quasi-holes, just similar to the Tor code. Just in this case, there will be a U1 symmetry, which is absent in the Tor code, so the transition will be different.
Okay. All right, let's thank the speaker again.
Thanks.